In section 7.2, we look at something called substitution, which is sometimes called U substitution, because U is typically the variable used. And so we're going to do more integration rules, but we're actually going to be using a lot of the rules from section 7.1. But the thing about substitution is, like I've mentioned before, with integration, there is no quotient rule and there's no product rule. So if we have something that's more complicated than the rules that we've already seen in the previous section, then we need to use something called substitution, which is equivalent to, in terms of derivatives, the chain rule. So it's kind of like the chain rule of integration. So the first rule here is just a reminder of the chain rule, which is basically that if we're taking the derivative and that inside part of the function is more complicated than an x, so for example, if instead of having something like x to the fifth, we had something like 7x squared plus 3x to the fifth. The idea is that we can, the first part of the derivative is the same in either, which the chain rule is saying take the derivative of the outer function, which in either case here is something raised to the fifth power. So if we take the derivative of x to the fifth using the power rule, that would be 5x to the fourth. So if we do the same thing with this more complicated expression here, it would be 5, but instead of the x, that's the more complicated part, we leave it alone, 7x squared plus 3x, and then the exponent becomes a 4, just like that previous example. And I should mention here what I was labeling is this inside part is the g of x, and the outside part, in this case, is x to the fifth, or something raised to the fifth power. The chain rule says, though, that once you do that, when you're dealing with the inside part being more complicated than just an x, you have to multiply by the derivative of that part. So the derivative of g of x. So in this case, that would mean multiply by 7 times 2x to the 1 plus 3. So that's just a review of the chain rule. I could simplify that, but I'm not going to go any further with that example. But we could go ahead and let's just try out this next example here. So remember our notation, d over dx means take the derivative with respect to x. So in this class, at this point, we've talked a little bit more about the variables matching up. Taking the derivative with respect to x just really means take the derivative as we normally would, because x is the variable that we're working with in this problem. So let's take the derivative. So that would be, you could even rewrite this as, instead of dividing by 5, you could say that it's 1/5 times 5x squared plus 8 to the fifth. So the 1/5 is like a coefficient in the front. So then if we apply the chain rule, we would bring down the 5, becomes x squared plus 8. The new exponent is 4. And then the last part of the chain rule is to multiply by the derivative of that inside part, which in this case is, oh, I realized I put my parentheses in the wrong place here. So 5x squared plus 8 is that whole inside part. Oh, I see what happened here. There's too many 5s in this problem. Okay, so I brought the 5 down as part of the power rule, but the part inside the parentheses should be 5x squared plus 8. So now I have to multiply, the last part of the chain rule is to multiply by the derivative of that inside part, which is 5x squared plus 8. So that's going to be 10x. So if I go ahead and simplify this, here we've got 1/5 times 5, so that can cancel out. So it ends up being 10x times 5x squared plus 8 to the fourth. And I would leave this as my answer. I mean, I can't distribute that 10x because of the exponent of 4. So if I wanted to do that first, I would have to evaluate that exponent of 4 first, which would mean 5x squared plus 8 times 5x squared plus 8 times 5x squared plus 8 times 5x squared plus 8, and I don't want to do that. So this is going to be our simplified answer here. So now, remember with integration, it's working backwards. So if I wanted to integrate 5x squared plus 8 to the 4th times 10x, the answer, because this is what we got when we took the derivative of that part, is going to be what we had started with there. 5x squared plus 8 to the 5th over 5, or times 1/5, however you want to write it. And since we are integrating, I am going to go ahead and add that plus c at the end. So this is the answer. So the reason I took the derivative first was to kind of show you, yes, this is the answer because we've already kind of checked our work, which is if we took the derivative of this part highlighted in yellow, we would get to 10x times the 5x squared plus 8 to the 4th power. The thing is that how do we know to get from here to there? And that's going to be using something called substitution. So one idea of substitution, one thing when you're dealing with an integral that might trigger in your mind, okay, I could use substitution for this, is if you see an expression and you also see its derivative present. So if I do some highlighting here, in this case, you see we've got 5x squared plus 8, so that expression. But then the derivative of that part highlighted in blue is 10x, so its derivative is also there. So that is one kind of clue that you can look for in a problem that means to try substitution. Let's look at this example. If I try to simplify this problem, this is very similar to a problem that's just x cubed. And if we had x cubed and we were trying to take the integral, we would use the power rule for integration. And we can do the same thing here, but we are going to need to break it up in steps. So the way that use substitution works is first, it's really to find that inside part, just like what we would normally think of as our g of x, but I'm going to label that as u. So in this case, u is equal to 4x minus 1 because that's the inside part of the function. Same thing that we were looking for when we were doing chain rule. And then the outside part of the function, we're going to actually deal with that later. But that's normally maybe what we would call our f of x. So here we have our u that we've selected. Now we're going to take the derivative. And so using the notation we've talked about so far, we would say that the derivative of u with respect to x is going to be 4. And now this is important though, is that I need to get du by itself. And so I'm going to multiply both sides by dx. So I have that du is equal to 4 dx. So I've got this was the first part of the substitution, and based on the u I selected, this is what du is. So what we're actually going to try to do is we're going to try to rewrite our integral now all in terms of u with no x's. And that's what we're going to take the integral of. So how do we do that? So let's say equal here. Let's start to do our substitution. So integral. So this is 4x minus 1 to the 3rd power. So using our substitution, 4x minus 1 is the same thing as u. So I'm going to write it as u cubed. And we can't forget about this notation, which, you know, perhaps for the first section, we might have just kind of ignored it and just known that for integrals, it's kind of just there. But we do need to use it with these substitution problems. So now we have to rewrite dx here, and I'm realizing that I didn't write this down correctly. So let me go ahead and erase this. I had said it that when we had du over dx is equal to 4x, we could get du by itself by multiplying both sides by dx. I just wrote that for some reason as x instead of dx. So this is what it should be. So now I need to figure out what to plug in here. And you could, if it helps, you could actually rewrite this expression here. If we had wanted to get dx by itself, we could divide both sides by 4. So that means that dx is equal to du over 4, and so then we can plug that in. So dx is the same thing as du over 4. So what we've done is we've rewritten our entire integral now with u's and no x's at all. It's a little messy as it is right now. I'm going to kind of simplify it. So the du over 4 is really just the same thing as 1/4 times du. And since 1/4 has no variables attached to it, we can treat it as a coefficient. And one thing about integration is you can actually bring it to the front of the integral sign because it doesn't affect our derivative. It's just, our integral. But once we take our integral, the last step would be to multiply by the 1/4. So I'm going to bring the 1/4 out, and then we've got u cubed du. So now this has set up something that should look similar to what we had done in the previous section. So the thing I have that's raised to the 3rd power is now just a single variable u, and I can, because of that, now go ahead and just use the power rule for integration to solve this. So now let's integrate. So it's going to be 1/4 times, using the power rule, u to the 3rd becomes u to the 3 plus 1 over 3 plus 1. The du goes away when you take the integral, but then we do need to add that constant c. So simplifying a little bit, we've got 1/4 times u to the 4 over 4 plus c. Simplifying a little bit more, we could rewrite this as u to the 4th over 16 plus c. So we're pretty much done at this point. The thing is that our original problem had no u's in there. That was something that we had introduced to the problem. So the last step with any substitution is to go and substitute back. So in this case, to replace any u's with 4x minus 1. And that's going to be our final answer. So it's going to be 4x minus 1 to the 4th over 16 plus c. And I don't have much space on here, but I am tempted to just show you how you could still just check your work, which is you just can take the derivative of this. So if you try to check, take the derivative. If we did that for this problem, we're going to use the chain rule to take the derivative. So it would be 1 over 16 times, and then the derivative of 4x minus 1 to the 4th would be 4 times 4x minus 1 to the 3rd, and now the chain rule part is to multiply by the derivative of the inside, which is going to be 4. The c, when we take the derivative, goes to 0. So then if we simplify this, you end up with 4 times 4, which is 16 in the numerator, 16 in the denominator, so that cancels out, leaving 4x minus 1 cubed, which, if we check, was exactly the function that we were originally trying to take the integral for. So that tells us that our integral is correct. Now let's look at this example. So with this example, there's a little bit more going on. You might not be able to see which integral we are going to end up using, whereas with the previous example, you might have noticed something cubed, and so that we were going to end up using the power rule for integration. It might not be as obvious with this one. But again, that clue I was talking about looking for, really that is to help us figure out what to set u equal to, is if we can see a function and we also see its derivative present. And so that's what helps us figure out what u is. So when we first look at this, if we're trying to take the integral, if it were derivative, we could use a quotient rule, but that's not an option for us with integration. And so it means we have to try and simplify it some way. And so the way that we simplify it is with substitution. So we want to try and identify a u. What should u be for this problem? So sometimes it's looking for the most complicated piece. but it does help if you can also see its derivative there. So I'm kind of pausing. Maybe you're thinking about what you want to set u equal to. For this problem, we'd actually set u equal to 2x cubed plus 7. Why would we do that? Well, it is the more complicated piece and it has that exponent, so that kind of falls from the last example that we did. But it also, if you look at it, well, what is the derivative of 2x cubed plus 7? The derivative is 6x squared, and that's also there. So that points to the fact that that part circled in blue is probably our best bet for u for this problem. So let's let u equal 2x cubed plus 7. And now let's take the derivative of u with respect to x, which is 6x squared. And then we want to isolate du. So it is the same thing as 6x squared dx. So we've got u and we've got du. And now we want to rewrite our integral with just u and du in the problem. So for the u part, if I tried to rewrite that, I'm going to do the integral in the denominator right there. I guess I don't even need parentheses. I could rewrite that as u to the 3 over 2. And now for the last bit, there's two different ways that you could go about this. One thing you could do is to perhaps notice that right here is 6x squared times dx, which is exactly what du is. So I could just go ahead right there and just put a du because of this whole part right here. Sometimes they don't always match up exactly like this. Another way to put the substitutions in is to actually get dx by itself. So this is something that you could always do for these types of problems, which in this case, to get dx by itself, I could divide both sides by 6x squared, which means that dx is equal to du over 6x squared. So if I tried to do the substitution at this point, I'd still have in the denominator, once I substitute in the u to the 3 over 2 in the denominator. If I do it this way, getting dx by itself, I actually wouldn't do anything with the 6x squared. But then I would just say I have now a dx. Let me go ahead and plug in what dx is. It's du over 6x squared. And if you've selected the correct u and your derivative is correct, what should happen is that if you have any x's in there, with this technique, they should all cancel out, which is actually what happens here, because we end up with 6x squared over 6x squared. So we get basically the same thing, which you could say that it's du over u to the 3 over 2, or you could write that as, I'm running out of space here, so let me just go up to where I originally wrote the substitution. You could also write this as 1 over u to the 3 over 2 times du, which is probably a better way to write it, because when we take the integrals, usually we think of that du or dx as just kind of off to the side, and it's not really something that we look at when we're taking the integral. At this point before we actually take the integral, it's always good to check to make sure that you have no x's left in your problem. So here it's just u's, all the variables match, which means we can go ahead and start to integrate. Before I do that though, I'm going to rewrite it a little bit more, because 1 over u to the 3 over 2 is the same thing as u to the negative 3 over 2 du, and now it's set up to go ahead and use the power rule for integration. So that's going to be u to the negative 3 over 2 plus 1 over negative 3 over 2 plus 1, and then plus c. So here I go ahead and add my fractions together. Common denominators always help out here. So simplifying this, we get u to the negative 1 over 2 over negative 1 over 2 plus c And I'm going to go ahead and keep simplifying, and to have more space, I'm going to go ahead and delete this. Erase this stuff on the bottom here. So this is the same thing as whenever you divide by a fraction in the denominator, you're dividing by a fraction. It's the same thing as multiplying but by the reciprocal, which means changing 1 over 2 to 2 over 1 and turning it to multiplication. So that's negative 2u to the negative 1/2 plus c. So we're not quite to our final answer yet because we need to substitute back into x's. So that would be negative 2 times, and instead of u here, we'll put 2x cubed plus 7 to the negative 1/2 plus c. This would be our final answer, and you could check your work by going ahead and taking the derivative of this part in yellow. And then before I go to the next example, I'll just show you, you could rewrite this a little bit. So the negative exponent means that I could move that part to the denominator. The 1/2 means I could convert it to a square root. So this is actually the same thing as negative 2 over the square root of 2x cubed plus 7 all plus c. That's another way to write the final answer. Here's another example where we wouldn't be able to take the integral unless we do substitution. So we want to look for the more complicated piece. Unlike the previous two examples, we don't have something in parentheses, so you might not be sure what to set u equal to. So we would go ahead and look for really the more complicated piece, which in this case I would say that's the denominator. And then if we check, well, what's the derivative of that? The derivative of that is 6x squared, which is what we get in the numerator. So that tells us we should probably let u equal 2x cubed plus 7. Now let's go ahead and take the derivative, which is 6x squared, and then isolate the du. That means that if we let u equal 2x cubed plus 7, then du is equal to 6x squared plus dx. And then now let's go ahead and make that substitution. So this is really similar to the last example. So here, this whole thing matches exactly with du, so I'm just going to replace it with a du. And you can put the du in the numerator here, or you could say 1 in the numerator times du, and that represents the same thing. I'm going to write it in the second way because it makes it easier, I think, to see and take the take the integral. And in the denominator, we just had 2x cubed plus 7, which is what we let u equal. So here we've got the integral of 1 over u du. It's all been converted to u's, so now we can go ahead and try to integrate. If you see this at first, you might be tempted to, u to the 1. You could write it as u to the negative 1. If you try to integrate using the power rule, that gives you something weird. This is weird because this is actually not how you're supposed to integrate it. So I'm going to go ahead and erase that. This, in either way you look at it, this is not when we use the power rule. There's a special exception to the power rule, which is that if it's in the denominator with an exponent of 1, this is a natural log integral rule. So the way that we integrate 1 over u, or u to the negative 1, is to say ln of the absolute value of u plus c. And then I will convert it back to x's. So that's ln of 2x cubed plus 7 plus c, and that's the final answer. And if you did take the derivative of this, the derivative of ln of something is that we'd put that something in the denominator. So that's why we've got our 2x cubed plus 7. And then the last part of the derivative rule is to multiply by the derivative of that argument of ln, which is why there's a 6x squared in the numerator. So I'm just kind of talking about it, but if you did actually write out all the steps to take the derivative to check your work, you should get right back to that original function that we had to take the integral of. Let's try one more example. So again, I feel like it's worth noting if you had seen something like this and you were asked to take the derivative, you would use the product rule. But there is no product rule for integration, so that's not going to work here, and that's when we would try instead use substitution. So what do we set u equal to in this part? So it looks a little different than the other examples that we had seen. The choices here be kind of like here or here. And without doing much work, because there's that e in there, there's a strong chance that the integral rule we're going to have to use in the end is the exponential integral rule. So in order to use that, though, we would actually let u be the exponent, which in this case is 2x cubed. And that makes sense from what we've talked about already, because I would say the 2x cubed is more complicated. I don't know if that's the right word to use. But you could say, well, if I take the derivative of 2x cubed, I get 15x squared, which is also there. And so that means that setting u equal to 2x cubed is a good substitution to try. So now let's take the derivative, du over dx is equal to 15x squared. I'm going to get du by itself. So that's 15x squared dx. And now I want to start making some substitutions here. So this is equal to the integral of, if we look here, that's going to become e to the u. And then if we look at the rest of it, we actually have 15x squared times dx, which is exactly what we said du is equal to. So I'm going to multiply this by du. And now let's integrate. Well, the integral of e to the u is e to the u. Because we're integrating, we'd also have a plus c. Last step to substitute back. So we get e to the 2x cubed plus c, and that's our final answer. And if you check by taking the derivative, you'll get back to the original function that we started with.